This video lecture is talking about entropy and thinking about what entropy really is and how we can measure it and how we can isolate it and tie it to other thermodynamic things. Entropy is abbreviated S. Clausius was thinking about there's a significance of the ratio of heat and the temperature at which it's delivered. And he came up with an equation where he talked about entropy had to have some sort of tie to Q over T, and we're thinking about the system here primarily as we think about that. Also think about reversible processes. That's how he was thinking about it when he first started dealing with it. Entropy, again, when we think about this T value, this has to be in Kelvin, so you'll have to do conversions with that. Remember, we're talking about the system and what has to happen to it over time. If the system is going to freeze, it's got to lose energy. If it melts, it's got to gain energy. So that's all kind of part of the thermodynamics discussion here. Entropy is thought of as a measure of the amount of randomness in a system. So again, solids would have less randomness than a liquid. A liquid would have less randomness than a gas. If you think about putting that onto some sort of continuum, and you think about entropy and how things are labeled, you think about solids with their particles packed together, and then we move to liquids, and then we move to gases, we would have the most S here in terms of entropy, because gases have the most random molecules to think about. It is related to these motions of molecules. The more motion you have, the more random you are, the more entropy that you have. It's a state function. It's like E. Talk about the total energy of the system we talked about in 19.1. It's also thought about as a state function like enthalpy and H. So we can find the change in entropy by doing delta S is the S final minus the S initial. We can look at the overall disorder and how that changes for a particular system. That's the equation to look at. We can also think about it as an enthalpy change. So if we want to think about delta S here, we can take the Q of the reversible process that we may have over absolute temperature. That's one possible way to think about it. We can also think about Q in terms of enthalpies of fusion. So we can also think about delta H of either fusion or vaporization, and we can find the randomness or the disorder that would happen for it. An example of this in terms of disorder is thinking about the idea of mercury going through a heat of fusion idea. If we ended up with mercury with a temperature of 234.1 Kelvin and its heat of fusion was equal to 2.29 kilojoules per mole, and we knew that we had 50 grams of mercury that we wanted to melt, we could talk about what would happen to it in terms of the heat of fusion. Or actually, we're going to melt it down in terms of fusion to try to separate it. How much entropy would we really need to have? A couple things about this problem to think about. We know that we have the delta H of fusion going on here. It is an exothermic process. So if we're going to take and melt this, the energy is going to leave from the system and go to the surroundings. So this value here of delta H is going to be negative because that means it's released out within this in terms of melting. Freezing is the reverse of melting. The enthalpy change, think about the heat of fusion being a minus. So melting would mean that the energy goes in. This is freezing. We've got heat of fusion. It's opposite of that, so it's minus. So that's what makes it a little confusing. So it's opposite of fusion, so we got to use, we're melting it, so we're going to do negative 2.29 kilojoules per mole when we solve it. Again, it's exothermic. The energy is leaving the system and moving out to the surroundings. So since this is in moles, we've got to do a conversion. Grams of mercury into moles of mercury. And that's the molar mass. And the molar mass of mercury is 200.59. So the grams of mercury cancel. So when we get finished with that, we get 0.249 moles of mercury. Now we have to use that 2.49 moles of mercury because we have to convert that into kilojoules of energy. So trying to convert that, clean this up a little bit. from our table of variables, we're going to take the 0.249 moles of Hg, and we're going to convert that into kilojoules by using that heat of fusion we had earlier. We know that for every 1 mole of mercury to go through fusion, that would be 2.29 kilojoules of energy. Now we also know that when we deal with this, we're going to also have to get it to joules eventually, because that's the standard condition. So we're going to go kilojoules into joules, 1,000 joules in 1 kilojoule. Moles of mercury cancel. So when we get finished with that and we're trying to figure this out, we get 0.570 for a number, 0.570, and the units that we're left with are going to be joules of energy that we're dealing with. Trying to calculate it out. Once we convert it into joules of energy, that tells us how much is going through fusion. Again, when we think about this being with fusion, this freezing value is exothermic. So what we're doing is we're getting this Q value, we are transferring energy out. So it's a negative value is the energy that has to leave for in order to freeze. So it's going from a liquid to a solid. So now we have to figure out how that works with entropy. The entropy is going to be equal to our energy value that we just had, which was the and we had to, this was 570 joules when I multiplied. Negative 570 joules, all divided by the absolute temperature, which was 234.1 Kelvin. So the entropy of this, when this would freeze, is going to be a negative 2.4 joules per Kelvin. So the disorder decreased because it went from mercury as a liquid down to mercury as a solid. There is less disorder. And again, the key part to that is realizing this heat of fusion, that's melting. Well, we're freezing it, so it's opposite of that, so the sign becomes negative. So if that's melting, freezing has to be equal and opposite in terms of sign. So the entropy would go down to negative 570 joules. When we think about other problems with this, that leads us to our second law of thermodynamics. First one, we talk about how energy was conserved, but it could be transferred, and it was related to the Q and the work that was done. The second law of thermodynamics talks about the entropy of the universe is going to increase for any spontaneous process. Entropy of the universe does not change for a reversible process. Now, thinking about spontaneous things, remember they only go in one direction if it's spontaneous. So mathematically looking at it, the delta S of the universe, if the system plus the surroundings equals 0, there's no change in entropy. That's only true for reversible things. Again, that's where we don't have any work done, we don't have any changes in the original conditions, not usual to happen. Irreversible processes, which are spontaneous, the system of the universe is equal to this delta S of the system plus delta S of the surroundings. These last truths mean that as a result of all spontaneous processes, the entropy of the universe must increase. So thinking about how this works with signage, with entropy, if delta S, thinking about the overall disorder, is positive, that means we've increased the disorder of the system, and that's thermodynamically favorable if delta S is possible. And that is for reversible reactions. If delta S is negative, some sort of outside thing has to have happened probably to make that happen. This would be usually a not spontaneous thing. This is usually a spontaneous thing. That's not all the time, but that's a general kind of rule here thinking about delta S. So temperature plays a role in this, enthalpy plays a role in this, but again, when you think about how this looks with enthalpy, with disorder, if it's an irreversible process, delta S of the universe should always increase. So even if you have this S of a system, even if the S of the system decreases, that means the S of the universe has to increase because entropy is always conserved. And if those two values sum together to give us a positive value, we think about systems or surroundings. If we put these two things together, you can have something that's endothermic if it increases the disorder of the surroundings as long as they sum together for the universe. So again, kind of back to summarize those values. we get delta S of the universe, if that is positive, that's a combination of the S of the system plus the entropy of the surroundings for a spontaneous reaction. If that becomes positive, we've increased the disorder. Several problems to do with this. See what you think about the format of the video lecture. See if you can see it and how it looks.